today we're very happy to have Mehtaab Sawney from Columbia, who will tell us about improved bounds in Szemeredi's theorem.
Thank you so much for the invitation. So I'll be discussing improved bounds for Szemeredi's theorem, and everything I'm discussing today is joint work with James Leng and Ashwin Sah. I guess let me discuss the problem let me define the problem we're talking about. So the definition is so let Rk of n be the largest subset of bracket n, by which I just mean the first n positive integers. So largest subset A, such that A has no k-term arithmetic progression. And by k-term arithmetic progression, I just mean so Kp is going to be the set is the configuration of the form x plus y to x plus k minus 1 times y, with y not equal to 0. And what I can understand is how does Rkn behave asymptotically? So maybe the driving conjecture here, which was formulated by Arithmetic and Theorem in 36, is they asked is Rk of n little o n. So in particular, if you take a positive density subset of the first n integers, are you guaranteed to contain a k-term arithmetic progression? So this has turned out to be a pretty impactful question. So the first non-trivial result due to Roth was that he could at least show this. So two-term arithmetic progressions are easy. He was able to understand the case where k is equal to 3. So he was able to show that R3 of n, not only was it little o n, but he was able to show the quantitative bound n over log n. The progress on this problem stalled for many years until Szemeredi proved his theorem. So the question of Arithmetic and Theorem was first answered for k equals 4 in 69, and in general in 75, and he showed that Rk of n is little o n. This was subsequently given an alternate proof by Furstenberg using ergodic theory. Two years later. But both of these proofs gave sort of extremely weak dependences on the little o n. So in particular, because of the use of ergodic theory, there was no quantitative rate here, and Szemeredi proof, you could ask like sort of what function do you save over the trivial bound of n? It's worse than any finite number of log, like any finite iterated log. So before just going further, I mean, so the special case k equals 3, we sort of always had a quantitative bound, and that bound was refined many, many times. So first by Szemeredi, then Heath Brown, then Szemeredi, then Bourgain twice, then Sanders, then Bloom-Sisask, and sort of very recently, so from last year, there was a result of Kelly and Mehtaab, where they proved that R3 of n, it's smaller than n times x pub minus log n to the 112. And this is a particularly remarkable bound due to what we know on the other side. So it was a result of Barand, a construction in 46, where you showed that R3 of n, this is at least n times x of minus c times log n to the 1/2. So in particular, up to changing this half to a 12th, we at least have the right understanding of R3 of n. But for longer progressions, sort of progress was much slower, and sort of we did have effective bounds until breakthrough work of Gowers So again, in 98, he handled the case k equals 4, and then in 2001, he handled the general case. He showed that Rk of n is less than n times log n to the minus 2 to the minus to that log n to some explicit power. And this is sort of the first reasonable bound. So in particular, he's saving some power of a double logarithm. And you couldn't extract such a savings from the proof. And this proof has turned out to be extremely influential, and we'll be discussing ideas in it. So in general, for k larger than 3, the only other progress on Gowers' bound was work of Green and Tao from 17, where they showed they could at least handle a case where k equals 4 and sort of get a slightly better bound. They could show something like n log n to the minus c for some small explicit constant c. And sort of the main result I'll be discussing today is an improvement to the work of Gowers, where we show that Rk of n, this is smaller than n times x of minus log n power ck. Ck in 0 to 1. Okay. This is still a slightly weird function to me, so we're saving more than any power of a log, but not as much as a 1 power of log. Okay. So what I really want to do is sort of discuss what the general philosophy is behind attacking these problems. So my motivation is sort of to explain the explain the approach to Rk of n via the Gowers norm. Sort of maybe discuss this problem is stated as a completely combinatorial problem. Maybe the thing that's pretty remarkable here is that there's some kind of underlying algebraic structure. And sort of how much algebraic structure you can squeeze out is sort of how good your bound is, and maybe a few morsels on the proof strategy. Okay, so I guess I'll start with defining what the Gowers norm is. Okay, so one extra comment, sort of throughout the talk for various reasons. The integers 1 through n are not as nice as like the group z mod nz, where you should think of n as prime. For various things, I will write z mod nz. Really, you can always replace them by n, and sort of for the purposes of these problems, these two things are the same object. I'll make this abuse consistent. So first I'll need the definition of a Gowers norm. So it'll be convenient to look at functions z mod nz for the complex numbers. Where I'll need the notion of a multiplicative derivative. So I'll look at, so delta h of f is going to be f of x times f of f bar of f times the complex conjugate of f times x plus h. And the Gowers norm is just the average of some repeated multiplicative derivatives. So the uk norm to the 2k power is the expectation over x, h1, hk, delta h1, delta hk, f of x. It's a slightly incomprehensible formula. The nicer way to do it is to see it by example. So the u2 norm is the expectation over x, h1, h2, f of x plus h1, f of x plus h2, f of x plus h1 plus h2. So I'm sort of taking my average over f over these like parallelograms. So notice that x and x plus h1 plus h2 equals x plus h1, x plus h2. So I'm taking my average over these 2D parallelograms for the U2 norm, the U3 norm's 3D parallelograms, and so on. So these enter the study of the KP problem via the following proposition. So I label this in quotation marks, but sort of writing it like this is certainly pretty Gowers. So let fi be functions from z mod nz c, which are one bounded. Yep.
Do x, h1, h2 all range over like z mod nc?
Yeah, they're all yeah. So all so they're all ranging over z mod nz. In general, all my variables will be ranging over the whole cyclic group.
The expectation with respect to the uniform
Yeah,
measure.
so it's expectation with respect to the uniform measure. I'm literally looking over all parallelepipeds. So the relation here, so I'll take one bounded functions, and okay. It seems natural that if I'm going to study, say, 3-term arithmetic progressions, I might want to understand when the following average is large. So I'm taking the average over x and d of f1x, f2x plus d, f3x plus 2d. Term arithmetic progression. Suppose I know this is bigger than delta. What we'll be able to show is that the U2 norm of f3, say, that this is bigger than delta. So I've converted from, okay, I also didn't say this, it's not obvious this is a norm. The proof is many applications of the Cauchy-Schwarz inequality, a flavor, I will sort of give a flavor of these proofs. Okay, so let's sort of see what happens. So first, I'll do this manipulation quickly, but it's useful to see that sort of, in some sense, nothing too deep is happening. So I'll apply the triangle inequality. I'll get f2 of x plus d, f3 of x plus 2d. So I've just applied the triangle equality and used that f1 is one bounded. I can then apply Cauchy-Schwarz. Or I can use Cauchy-Schwarz to say that I can sort of square the inside. Okay. And so I have this average over d and I've squared it. So what I can do is I can sort of expand the square out and take an average over d1 and d2. So this is the same thing as the average over x, d1, d2 of f2 of x plus d1, f2 bar of x plus d2, f3 of x plus 2d1, f3 of x plus 2. So I just expanded out the square here. And if you do a change of variable, it turns out that this is the same thing as the average root somewhere. I'll lose square roots at some point. And you can just do a change of variable and you'll find that, sort of observe that this kind of looks like a multiplicative derivative. If you take d1 minus d2 and set it equal to h, it's sort of a multiplicative derivative up to a shift. And if you do a change of variable carefully, you get the following expression. And if you do Cauchy-Schwarz one more time, sort of you apply the triangle inequality to kill this term, and you do Cauchy-Schwarz once again, you'll find that this is bounded by the U2 norm. Okay. It's also important that you follow that computation. What's important is that by finite applications of the Cauchy-Schwarz inequality, I'm able to prove that if this kind of average is large, this U2 norm is large. So, okay, great. So I know this norm is large. Can I do anything with So what I'm going to do is sort of maybe sketch what Roth's proof looks like in this language. And writing it this way, sort of the starting point of Gowers' approach. So let's look at the proof of Roth's theorem. Okay, this is also an amusing thing. So when one is doing additive combinatorics and says Roth's theorem, they mean this and not obviously much more famous transcendence results. So slightly lie. So I have A, which is a subset of Z mod n Z. And let's say the size of A is alpha times n. And A has no 3 APs. Don't worry about wraparound issues. I'm not going to be so careful about it. So what does this mean? So we know that there are no 3 APs. So the average over x and d of the indicator function of A evaluated at x, the indicator function of A evaluated at x plus d, and the indicator function of A evaluated at x plus 2d, this is equal to 0. I'm just writing down analytically what it means for the set to have no 3-term arithmetic regression.
Almost equal to 0.
It's not actually equal to 0 because it's the, so if you take d equals 0, okay, this gives you some trivial term, but it ends up not mattering. Let's not figure out it too much. You can write this 2 different ways. So what I'm going to do is subtract off the average. So I can take the average over x and d, the indicator function of x, indicator function of x plus d, times alpha. And if you evaluate this, this turns out to be alpha cubed plus the expectation over x and d, the indicator function at x, the indicator function at x plus d, and this sort of balanced indicator function, the indicator function at x plus 2d minus alpha. So I know 0 equals something kind of large plus this term. This now lets me apply the theorem at the middle board. I get something useful. So I can sort of use that last line plus the proposition, or the theorem as it's labeled. What I get is that the indicator function of A minus alpha, its U2 norm to the 4th power, this is bigger than some power of alpha. I'm not going to track it so carefully. Okay, great. So at this point I've just told you this. This doesn't seem immediately useful. So now I get to pull a rabbit. So the U2 norm for any one bounded function has a very beautiful Fourier interpretation. So you can just take it, you can take psi over the dual group. This is just the L4 norm of the Fourier transform. And once a formula like this is written down, you can just evaluate it directly. This can just be checked by orthogonality identities. And in particular, this you can use Parseval and say that this is bounded by the maximum over psi of f hat of psi squared. Okay. So now let's rewrite out this condition given this formula. What this tells us is that there exists psi such that the expectation over x of the indicator function of A minus alpha evaluated x times, I'm going to use the number theorist notation, e to the psi x. This is bigger than alpha to some power.
Getting a founding of sum of 4th powers in terms of a
Okay.
square, like if you scale out by a constant, isn't that?
So certainly this inequality is true. And yeah, you can use Parseval to say this is bounded by 1. You need to be careful. So we have that this balanced function correlates with some Fourier character. And what you can do is you can use this to say A has increased density along a arithmetic progression. So basically, you can find some arithmetic progression of, it turns out, of size like square root n, and A will turn out to have, so because I know the average density correlates with this character, you'll sort of be able to show that A has increased density along this progression. And that will close the argument, so you just keep on iterating this argument. And the density can never, go above 1, and so eventually you get a contradiction. The contradiction eventually comes from this you have to track what this approximately equal to 0 means. But yeah, so that sort of completes the proof. I'm obviously omitting a lot of details, but I just want the flavor of what's happening. And so maybe so what is the key step in this argument? The key step is star. That's sort of where I extracted some structure about my set. I got that it correlates with a Fourier character. So it turns out you can sort of try to run this strategy for longer progressions, and that's what Gowers did. So, okay. So if your set has no KAPs, then it's relatively easy to show that the indicator function of A minus alpha, the UK norm, this is bigger than alpha to some power. The issue is star no longer works for K bigger than 2. So I'm not able to use Fourier analysis to sort of derive a useful conclusion from this. And I need to be able to derive some useful conclusion. And okay. So what Gowers does in his work is he says, okay, he's able to extract some structure. What he says is that there's some very long subprogression where A has increased density. It turns out, for our purposes, that that's sufficient to prove a bound on Szemeredi theorem like he did, but that's sort of not what we'll be aiming for. So we'll be aiming for sort of a more algebraic description of what's happening. So what we'll be left with is trying to understand if we have that F UK, this is bigger than some delta, what can we say about F? Okay. So delta is hard. Let's try to understand what happens when it's equal to 1. So if you know it's 1, then you know we'll consider throughout the rest of the talk, F will always be 1 bounded. So we'll be considering F, which is say norm 1, and it's the exponential of some function g of n. Okay, so let's try to see what happens when the U2 norm is 1. You can sort of, if you sort of chase definitions, this means that for any h1 and h2, that delta h1, delta h2 of f of x, this is equal to 1. So I will introduce one extra piece of notation, which is the additive derivative. The additive derivative is going to be g of x minus g of x plus h. Okay, so this condition that this is equal to 1 for x, h1, and h2 means we have that del h1, del h2 of g of x, that this is always equal to 0. So what am I saying? I have a function g such that if I take two derivatives, it's always equal to 0. And so this tells you that g of x, this is a linear function. Cx plus d mod 1. And this sort of recovers the prediction of Fourier analysis. A phase is exactly, up to shifting by some complex number, a phase is exactly a linear function in this sense. And you can try to do the same thing. So you can look when the U3 norm is equal to 1. In the same setup, you'll get del H1, del H2, del H3 of g of x, that this is equal to 1. Oh, sorry. I have a function that's second derivative always vanishes. Again, elementary to show that g of x, in this case, is a quadratic. I mean, this at least suggests there's some algebra happening. The issue is we don't actually care about exact solutions. We don't care about when f is equal to 1. We really, for our application, we really want to understand when the UK norm is bigger than some like small constant. It's not close to 1. Like, this is what's called the 100% regime. And it turns out if you make this 199, like 0.99, it turns out that all examples are very close to quadratics in some appropriate sense. What you want to be able to understand is what happens when delta is a small constant. And okay, so when we did Fourier analysis, we sort of this star, what it tells you is that there's essentially no different examples. You're still correlating with one of these 100% examples. Unfortunately, the unfortunate reality is that that doesn't hold true for higher norms. And sort of, we'll do it by example. So let's look when FU3, let's say, is 0.001. The relevant example, it turns out, is g of x. The simplest example C is root 2 times square root 3 of x. And what I'm going to claim is that, okay, so interpret root 2 suitably in Z mod n Z. Treat it as an integer for now. This is easier to do over integers. What I'm going to claim is that delta H1, delta H2, delta H3 of g of x is equal to 0 for a positive portion of H1, H2, H3, x. So I range over all possible values for a positive portion of these. This will be equal to 0. This is a computation. I'll do it. Let's see how this goes. I'll try to do it live. So the idea will be the following. So if I have two real numbers x and y, the floor function will equal x plus y up to some integer in 0, 1. And if my integers are sufficiently generic in some sense, then it'll be 0 like half the time. So let's compute del h of g. So this is going to equal, I'm going to sort of negate this, or let me negate this. So if you do it carefully, it's root 3 x plus h. This equality means it holds a positive fraction of the time. This is going to be equal to root 2h times floor of root 3h plus root 2h times floor of root 3x plus root 2x times root 3h. Okay. You can now do this one further time. You can look at del h1, del h2 of g of x, and sort of assuming that, say, this formula always holds. If you do it out, what you'll find is that you'll get some formula that will only depend on h1 H1 and H2. And the reason is sort of, we went from something that's quadratic in x to something which is linear in x, like a positive fraction of the time. And when I do this one further time, it'll be like degree 0 in x, a positive portion of the time. And if I take one further derivative, then it'll be 0. So you can, in theory, write the whole theory like this. This is some bracket example, and it turns out that the following inverse theorem is true, that if f is, like, the U3 norm is bigger than some delta, then you correlate with an exponential phase of some bracket polynomial. So maybe you don't have one term like this, but you have the sum of many of the terms, some bounded number of like floor functions like this. This is not a particularly nice description. It turns out the better description was really discovered in organic theory. So really, this was discovered in the theory of what's called non-conventional ergodic averages, so work of Furstenberg Weiss, Kahn-Blazin, Post-Kra, Ziegler. There's several other names. These names are certainly important. Really, what you should be doing is you should be viewing this as an example coming from a nilpotent Lie group. So I'll be extremely concrete. Let me sort of explain where this example arises. So I'll be considering the simplest nilpotent Lie group, so the Heisenberg group. So it's a set of 3x3 upper triangular matrices with 1 on the diagonal. I can look at the commutator sub. So this is nilpotent of degree 2 because the commutator subgroup is, you just have R in the upper right corner, and so if you take one further commutator, it'll vanish. And what I'll be considering, some discrete co-compact subgroup, so gamma. I'll take quotients on the wrong side. Apologies in advance. So let's consider an element G, which is 1 ABC. So I can just define the function capital F from this group to C in coordinates. So I can say f of G is equal to E of minus A or B plus C. So that's a perfectly well-defined function on the group. It turns out this function is nice. So what turns out to be true is that f of G times gamma is equal to f of G for gamma in the lattice. And so really you can think of f as a function from G mod gamma to C. So at least this gives you some natural, so this sort of tells you that you can think of these like floor function, these say bracket, what I like to call bracket quadratics, they sort of come from this nilpotent Lie group. And it's actually even nicer, sort of, what you can look at is, it turns out the correct thing to look at is f of G of n. So I'm taking my element and raising it to the nth power. You can just compute what G to the n is for n being an integer, and you'll find that it's e to the minus an for bn plus cn plus a times b. So somehow I've given a very natural algebraic description to this example. And all examples for the U3 case will come from step 2 nilpotent Lie groups in this fashion. You'll just take some continuous function on G mod gamma, and you can sort of, this gives you a function. If your U3 norm is large, you correlate with such a function. Unfortunately, making that description precise is sort of rather technical. Main reason being sort of what properties do I require on F, what properties do I require on gamma, what properties do I require on G. All of these need to be quantified. And while that's important for a rigorous discussion, it's best omitted in setting. So I'll be sort of saying things colloquially in terms of bracket quadratics or bracket functions, but everything I say has an immediate meaning in terms of this more algebraic description. And when you're writing the proofs, you have to operate in this more algebraic description. Yes.
what the correlation statement means. That's because in the earlier version, like f was a function on x, and sort of the character was also kind of a function on x in some sense. But now suddenly there's like an auxiliary g.
So what I'll be considering is polynomial sequences. So so is the following a valid answer to the question? So I'll have like a correlation of the sort expectation of f of x, or so I'll have a statement of this form. It's greater than some function. So
on one side, n is kind of in the g to the n is not cyclic anymore. It's kind of going from 1 to n. There's not a wraparound on the g to the n.
Yeah. So I mean, the point is, it turns out you can guarantee f and g such that g to the n is like n periodic mod gamma. Yeah. So like all the nice algebraic properties you want can be made true. It turns out this is why Z mod somehow this is one of the very sad things about the proof currently. This is does not naturally come out of the proof at present. Yeah, this is the correlation statement.
You're saying when the U2 norm is 1, then it's like literally like then like f has the form like exponential of like a quadratic or something. Is it like exponential?
Yeah, sure.
Or is it like some sort of threshold thing where like as soon as you're strictly less than 1, you get all these bracket things, or like?
So there's some number less than 1 above which you are supposed to correlate with a quadratic, and there's like some magic number at which point you start seeing sort of so that floor function equals 0 like half the time. So your correlation will be like a half or something. If there are like 10 brackets, your correlation will be like 2 to the minus 10. So so you'll above some threshold you'll only have real quadratics, but as this example gets more and more complicated, sort of the round off doesn't work as nicely, and sort of the correlation gets worse and worse. So sort of the real theorem underlying all of this, theorem should maybe be in quotes because this is rather imprecise. Due to Greentown Ziegler, this is in 2 papers. The paper in 11 dealt with the U4 case and called it the general case. So they sort of prove that this description is complete. So if FUK, this is bigger than delta, then there exists G, which is a bracket polynomial of degree k minus 1, such that 1 G has, so there's just some function of delta less than 1 terms. So what I mean here is like that expression has 1 term, there's some bounded number of terms, and 2, you have that, so f of x and the exponential of g of x for x and z mod nz. This is bigger than some function of delta of 1. So, even more informally, I have some bounded complexity object. Bracket polynomial is some bounded complexity object, and I have some amount of correlation. And algebraically, terms just really corresponds to like the dimension of the group. So a couple of remarks are in order. So due to the use of ultrafilters, so delta, like this less. So what I mean here is just some function of delta. These functions were ineffective. So that's one thing. The second thing is, even though this is ineffective as written, this actually does give you very powerful quantitative information. So they were interested in, this was the final piece in a program of Green and Tao to compute asymptotics for linear equations of the primes. So there's the famous Green-Tao theorem, which tells you that, let's say, there are arbitrarily many 5-term arithmetic progressions of the primes. Given this much stronger inverse theorem plus lots and lots of other work, you're able to actually give an asymptotic for how many there are up to n. So how many 5-term arithmetic progressions are there in the primes with all the n, 5-term arithmetic progressions with all the primes bounded by n. So this sounds slightly weird that it's an ineffective statement which gives quantitative results, but the ineffectivity is because you sort of don't know how fast you converge that. The main progress here so there's a big open question to give some quantitative bounds here. So Manners in 2018 gave some quantitative bounds. So he gave sort of less than delta to the O1 terms and some double exponential correlation and the key sort of thing that's hiding behind all these results is that we could sort of give much better quantification. We could get log 1 over delta to some power terms and correlation, which is, say, quasi-polynomial. And this is close to optimal. You certainly need log 1 over delta in the dimension, and you can't hope for correlation better than polynomial. So I'll give some hint of the proof. Mostly actually not a discussion of our work, but sort of so I'll briefly discuss the cases k equals 3 and k equals 4. So the proofs ultimately proceed, unsurprisingly, maybe by induction on k. So for k equals 3. So what's our starting assumption? So we know the U3 norm, this is bigger than delta. And I want to sort of derive some useful information. So I can sort of unwind the definition, take out one derivative. So I know that many multiplicative derivatives of f, they have large U2 norm. Okay, so now I can apply the U2 inverse theorem, which just says that I'm going to correlate with some exponential phase. So if you write it down, what you get is that delta h, so there exists theta h in R mod z, such that the following is true. So delta h of f of x times e to the theta h of x, this is bigger than delta to the O1. So unfortunately, at this point, there's something kind of problematic that's happened, is that these theta h's don't talk to each other. I've just applied the inverse theorem for each h individually, and I don't know anything about how these h's talk to each other. So the difficulty of the proof is getting these theta h's to talk to each other. So, okay, the first step is, so one can do a Cauchy-Schwarz argument. This is due to Gowers. So you can Cauchy-Schwarz a few times and eliminate this function f, and get some relation on these theta h's. What you'll get is that the expectation over h1 plus h2 equals h3 plus h4. The average over x of e of theta h1 plus theta h2 minus theta h3 minus theta h4 of x. This is bigger than some power of delta. Okay, so something, I'm hiding this argument from you, but something very useful has happened. I've eliminated this unknown function f, and I get this weird correlation statement. Okay, well, that insight is very simple. It's a geometric series. You can sum it. So what this means is that theta h1 plus theta h2 minus theta h3 minus theta h4, this is equal to 0, or okay, small or is equal to 0 1% of the time. I'll stop trying to track deltas. 1% is just some function of delta. So it's 1% of the time if h1 plus h2 equals h3 plus h4. Okay, so what do I have here? I have that the function h theta h, like, it respects additive tuples 1% of the time. This is a situation that additive combinatorialists are extremely happy with. So there's results of Bollock, Szemeredi, Gowers, theorems of Freiman and Ruja, which says we basically know what all functions like this look like. So theta h has to equal something like, has to equal some bounded number of terms, alpha I, times, by this I just mean the fractional part, theta I h. Okay. And this is actually extremely good progress. So, okay, you don't know that theta h equals this expression all of the time. You know it equals this expression 1% of the time, up to some small error. Let me hide those details. But I can just plug that in back there. So if I plug that in, what I'll get is that the average over x and h, delta h f of x, times e of alpha I h, or alpha I x, theta I h, this is bigger than some function. I get that my multiplicative derivative correlates with this kind of object. So it's alpha ix times beta ih. Okay, I mean, I'm not going to say too much more, but this is quite promising. I have something that looks like a degree 2 object, but I don't have that f correlates with it. There's an argument of Green and Tau, which sort of says you can take star. So you can upgrade star to a null sequence. And this is very clever, but essentially finite applications of Cauchy-Schwarz inequality. You convert this statement into the algebraic statement we were aiming for. Okay. Now I can explain why the proof gets harder for k bigger than 3. Okay, so the strategy I've written down actually makes perfect sense. So if we know that f u4 is large, then this implies that the average over h delta hf u3 norm, this is bigger than some power of delta. Okay, so I can apply the u3 inverse theorem And what I'll get is that there exist functions gh of x. So I'm not going to specify what these are, but these are bracket quadratic objects or degree 2 null sequences. And what I'll have is that delta h of f of x times gh of x, that this is large. This object where I take g mod, a function of g mod gamma, and I evaluate it at like a sequence g to the n. That's just the definition. Yeah, as stated, this is like a meaningless definition because you can encode any function. You needed to have bounded, like some kind of, needed to not be like a ridiculous function. Okay, and it turns out you can sort of run the same strategy. So the same Cauchy-Schwarz argument I omitted will give you the following. So h1 plus h2 equals h3 plus h4, the average over x of gh1 of x, gh2 of x, gh3 of x bar, gh4 of x bar is greater than delta to the over. This is good. And now, okay, so this is by the same Cauchy-Schwarz argument. Now there's this, now sort of the problem stares you in the face. So the first thing is, here on the inside we were summing a geometric series. And I know how to sum geometric series. The issue here is, the issue for the higher cases is that this is some kind of null sequence. And maybe the starting point, so the starting point of our work there's work of Leng, which gave improved understanding of equidistribution of null sequences. And this is sort of where the algebraic perspective really shines. So in the geometric series case, what are we saying? We're saying if e to the theta x is sort of bounded away from 0, that average, then the phase, this inner phase, is somehow very close to 0. You can sort of think of this as you originally had some function on the torus, and it's secretly actually a function on something one-dimensional lower. You need to quantify this. So there was some quantification given by Green and Tau, but the starting point here sort of was this improved was work of Leng, where sort of he was able to give better understanding of this equidistribution. It turns out you eventually need results of this type in full generality. So there was improved results on 1% linear functions. So I took this approximate statement. I said if this h theta h is equal to this some fraction of the time and some number of phases. We now have much better understanding of this situation, sort of almost optimal bounds, due to work of Sanders and Krutsisask. And that, for instance, was actually used in all of these works mentioned on 3-term arithmetic progressions, or ideas closely related were used. And so that's another input. But sort of, I mean, the main challenge is sort of, you have to solve some linear algebra problem. I'll just say one word about that. The basic point is that ultimately you can sort of ask, when is this average bigger than delta? So I have some nil sequence, I have when it's large. The point is, the only way this happens is if g of n projects weirdly on G mod deabelianization. G mod GG looks weird. And sort of, okay, this is an abelian group, so in some sense it's purely abelian condition. And I have this for these many tuples H1 plus H2 equals H3 plus H4. So I need to sort of glue this information together. And the heart of the main sort of new ingredient is sort of solving this approximate like, linear algebra problem more efficiently. That's what leads to the improved balance. And with that, that's all I have to say.
Questions for the speaker?
Do these improved bounds kind of give like information? Like, do they give like any control on the error term in green tau?
Yes. Yeah. So you can sort of you can save an arbitrary power of log. It's the same results as like what Vinogradov proved. So you can say count the number of k-term arithmetic progressions and save an arbitrary power of log. It also turns out to be useful for like qualitative questions. Knowing that you can save an arbitrary power of log means you can start inputting these ideas into like Ceph theoretic results.
So being like p squared plus nq squared.
Yeah.
Is play real.
Yeah. So I mean, so there was a result. So you was work with Ben Green where we used this result with many other ideas. So we could show that there are infinitely many pairs of PQ with PQ prime such that P squared plus 4Q squared is prime. And I mean, sort of what you use crucially here is that maybe the right way to write this down is there's sort of a naive, when you have the von Mangels function, it has certain very obvious biases. The primes are never going to be, they're not even except for 2. You can encode this in some very simple model function, which is basically just take the thing I said and make it slightly more elaborate. And you can show that that function and the von Mangels function are very, very close in Gowers norm. And to ever use something in like Ceph theory argument, it's very useful to be able to save an arbitrary power of log. And that's what's sort of used in this result.
Ask maybe one question. So can you just remind us, like, what are the best known upper and lower bounds for this?
So
largest set.
Yeah. So our k of n. So the upper bound I discussed is sort of n times x both minus log n to some power. And the lower bound is sort of embarrassingly far away. It's n times x both minus log n to it's some other power. I can't remember. It's not a half. It's slightly better.
And what do you expect is the actual?
So the truth is definitely the lower bound. And this is a kind of strange thing, right? Green tau theorems, in some sense, currently, or the proof uses at least a little bit of. It sort of uses something about the primes. I mean, in theory, the results of this form should have nothing to do with the primes. It should just be true on density grounds alone. Slightly strange fact that we can't show.
All these kind of theorems about primes are really just about the density of the primes.
So asymptotics are, you have to know you need more number theory. I mean, the green tau theorem uses very, very little, but you need to know good upper bounds for the primes. But yeah, I mean, in theory, it should just be that, there are n over log n primes. Yeah. And we now know that for 3-term progressions.
Equals 3, this is like, we actually get logs on both sides, right?
Yeah. So it's like the current bound, it's a half here and a ninth here. Or a half and a ninth.
So, and is there a chance that one can basically push those sequences on further to kind of get the truth, or are they explaining the actual truth?
So I think it's a delicate question. In some sense, the initial argument I showed by reducing to Gowers norms is slightly too lossy. It's quantitative lossy for this very particular question. I mean, this is sort of an if and only if statement. You know that the Gowers norm is large if and only, it's because it's an if and if statement. It's because it's an if and only if statement. sort of know these have to be there. There are various quantitative aspects which are not optimal. At present, I don't know if you could ever push them. The algebra definitely needs to be there. I don't know if the particular like ways we quantify complexity are certainly not canonical in any sense. And the proof, honestly, isn't either. So remains to be seen.
If there are no more questions, let's thank the speaker again.